we are talking about shaders programming in lighting. So, if I see the coloring of any primitive, pixel wise, then I don't need to provide the color at every pixel. We just need vertex position of the primitive name and colors and the model. It is a kind of a smooth model or flat model. That's it. And then it estimates the color. So if there are too many kind of vertices, then color will be smooth. If vertices are less primitives are there, then it will be coarse. But whatsoever. So the kind of the rasterization happens once we specify the color model and the color at the pixels. This is typical coloring in the kind of fixed function pipeline. Okay, in fixed function pipelining, if I don't want color through GL color, then still I want coloring. There is another way called lighting. There is another way called texturing. There is another way called texturing plus lighting. There is another way called blending. Whatsoever. Now we are talking about getting the color of a primitive through lighting. Okay, not providing GL color or whatsoever at the bottom. How it happens? Number one. Number two, in shaders problem. Number two, how transformation happens. I have a vertices. I have a kind of a model staying, and I am rotating, translating, transforming the light source. Or light source is stationary, and I am transforming the model. So one case is that how fragmentation for a lighting happens. I don't want GL color. And second thing is transformation, what model wise or light color. So these two things that we'll see. So idea is that if I have a light source, and so like in pipelining mode, fixed function pipelining mode, we need to specify the light source and their various properties like ambience and its kind of emission, its diffuse characteristics, and its kind of shining property. So these kind of properties I have to set for the model, I have to set for the lighting. So if I set, then OpenGL does all the calculations. But in the shaders programming, programmer has to do all the calculations. There is no light source, nothing. So what programmer is expected is that, like in shaders programming, there are two things. One is vertex estimation, and another is rasterization. Okay, so we say that at each vertex, what is its position at the end of all the transport? Each vertex, what is color? What is color? Color model is it smooth or flat? If I provide this information, then fragment shader would do the kind of whatever you want. So there is no OpenGL. In shaders programming, everything has to be done at the GPU. Means all the vertices transformation calculation, all the color calculation. If it happens to be GPU, GPU is kind of, it's dumb. So we have to write everything in the shader program. So how we can if I have a light source and if I have a vertices, then how we kind of calculate the lighting at the vertices, and then how it will go into fragmentation. That is the first thing that we'll see. Second thing is that transformation, that how transformation happens. Like if I need to transform the model, but I don't want lighting transformation. If I want to make a model stationary, I want lighting, means light source is moving. So these calculations are kind of complex in shaders program. It's not that straightforward. Like if I use the fixed function pipelining, everything is available. Push matrix, pop matrix, and you just rotate the light source, and then in the model transformation, push matrix, and when you do GL plus, everything is done. But problem with the kind of fixed function pipelining is very slow. If I have a kind of earth or aeroplane moving and these kind of, that it won't work. Means if vertices are in thousands, then we need to use GPU. If I need to use GPU, then GPU, the way it works is pretty much different. Means I have to, it doesn't know what is lighting and what is the texturing or whatsoever. So like okay, so in texturing, at least in fragment shader, we do something. But in lighting, it doesn't know anything light source or whatever. So how, like the way we specify the coloring at the vertices, how we specify coloring at the vertices when we do the light calculation. So there are two models in the light calculation. One model is called kind of Goard model, that is per vertex calculation, and one is form model, that is per kind of per fragment calculation. Like if I have number of vertices are less, then a form model makes sense. When like if we do per vertex per fragment calculation, then it will be smooth. Whereas a kind of Goard model is very nice if number of vertices are too many. Okay, so right now we will kind of focus on Goard model where we do the lighting calculation in the vertex shader. So if I do the lighting calculation in the vertex shader, means per vertex we are specifying the color that we calculate through lighting calculation, not through external kind of just GL color or whatsoever. So if I have a kind of a light color, if I have a material color, if I have a light position, if I have a viewer position, and if I have a kind of vertices location, if I have normal, how I can do mathematics in a way that the coloring parameter will generate at each vertex. If coloring parameter, if I generate at each vertex, and then if I know my kind of model, it is a smooth or it is a flat model, then fragmentation can happen. So right now in Goard model we will do the all computation at vertices. So if vertices are less, then lighting will not happen that nicely. But calculation are less. In the form model, the calculation is more because per pixel wise or per fragment wise we are doing the calculation, not at the vertices. But it makes sense if vertices count are less, at that time it would be smooth. If vertices count are many, then vertices calculation is okay. Okay, so we'll see the kind of Goard model, per vertices light calculation model in shader. Further to a discussion on OpenGL shaders in lighting. So we'll proceed on desktop. Okay, we'll go point by point. So shaders is kind of same thing what we covered in fixed function pipeline. Okay, so difference is whatever the API we are using in fixed function pipelining, so nothing is there absolutely, and it is moved to shaders code. Okay, so in lighting, light happens from two mode, that is light source and material reflection. Support RGB and color index, the lighting mode, and a vertex should receive the light. That is the idea. So we are talking about Goard model right now. So in Goard model, vertex should receive the light. Okay, in the smooth per vertex calculation will happen. Otherwise, flat per primitive calculation will happen. Light source position set after. So if after view matrix, if we specify the light position, then transformation is possible. Okay, so lighting, light, material and transformation. So this computation now shifted to shaders code. Okay, so light source, if we see, the light source has properties like position, direction and color. So where light source is positioned and what is its direction and what is its color. Same for the material also, its position and its normal and the color. Okay, so light source is of two types. This is kind of for the detailed discussion, the tutorial on the fixed function pipelining that can be seen. So one is directional one and one is kind of positional one. So from the position light emits and it comes from a direction. And if I place a cone, then light becomes a kind of a cone, a spotlight. Okay, light must fall on the vertices. If light is not falling on the vertices here and there, it doesn't make any sense. Light calculation would not happen. Okay, so how, if I say fourth parameter in the light position is 0, it becomes a directional light. Directional light comes from infinite distance. Like if I say 0, 0, 1, then light is kept at 0, 0, 1. Okay, but light would come as in parallel. Whereas positional fourth parameter light position is 1, but light will be kind of omni and it is kind of emanating from this position. So directional is kind of parallel light, like sunlight. Okay, so light calculation, so light has RGB component and material. So light source emits light and material has color. Okay, so light R and material R, G, light G, material G, and light B and material B, all three combined, then it becomes the kind of the each vertex light. So this is the mathematics. If multiple light source is there, then first we are done, then next we are done. So common thing is material. Okay, so if we take out kind of, if we combine this, then it can be kind of LR plus LR1 plus LR2 into MR, LG1 plus LG2, like that. So this is the light calculation at each vertex. So light from the R from the light and red from the material, green from the light, green from the material, and blue from the light, blue from the material. For each light source, it is calculated like this. Okay, now the light is kind of, it has three component, ambient, diffuse, and specular. For material also, it has four component, specular, diffuse, ambient, and emission. Okay, so there are two entity. One is light source that emits the light, and one is material which receives the light, and there is a third guy called light model. So light model is kind of it is a there can be many light source which emit the light, but light model will be always only one, and it has few properties like it also add to ambience. Then front side of the material and back side should be kind of lighted differently. The viewer is at infinite distance or it is near to the object. Our secondary color should be calculated after the shade, after the kind of once we finish the texture. So that is the idea. Please refer a tutorial on texture in fixed function pipeline. Okay, so ambience is kind of which adds ambience. So if there is no particular light, like if someone is working in night, and then if he is kind of bringing his hand, and whatever color he is seeing, when he sees, then that is the kind of ambience color, because there is no light source that is falling on the hand deliberately. There can be moonlight or there are other bulbs or tube lights or whatever. So ambience is the kind of environmental light. So how much it adds to environmental light, how much it adds to diffuse. Diffuse is the actual light of the material that will fall on the material, and specular is the shining. So like that, material has diffuse component, specular component, and ambience. It has emission component. So emission is kind of, if there is nothing specified, then what light it would emit, like a light source. So it won't be exactly like light source, but that is how it is. Please refer to the light model in the fixed function pipeline. Okay, so if model view is there set, then there can be transformation in light source and model. So light source translated where model is rotated. So if we specify model view matrix prior to kind of specify, so if we specify light source and model, or light source particularly after we specify the model view, then light source can also transform. That is the idea. Okay, so this is the calculation. If this is the surface like parabolic, and at a particular point, if this is the normal and this is the light falling at that point, this is the I and V is the tangent at that vertex. If these these four kind of attributes are there, then how it is calculated? So diffuse is the material diffuse color. So light diffuse, material diffuse, they constitute the actual color of the material. So actual color is only possible if light is falling exactly upon the kind of normal at the vertex, then it will be actual kind of bright color we see. Or if light is not at coming in the direction of the normal, at least light is at the angle, then it is dot. Dot means cosine of the angle. Cosine dot is nothing but what is the component of this light along n. So L dot n means what is the component of L along n. So if light is in kind of perpendicular, then there is no diffuse color, there is no color at all, because light is color perpendicular to the vertex, means there is no color at all. Okay, so this constitutes diffuse color, whereas specular will have L dot n and E dot n both. So where is the I? So if I see the color of a material, then where is L and where is N? If I see diffuse means, if I see the specular, means shining. So shining depends upon the I also. Like if L and N is perfect and I is at perpendicular direction, there won't be any shining at all. So there should be some angle between N and E, that is not 90 degree, and there should be some angle between N and L. So light direction, normal from the vertex, and I, all three. So N to E should not be 90 degree, and N to L should not be 90 degree. So L to N decide the diffuse color, and N to E and N to L, both together they decide the specular. Okay, so this is how it is. So there is a calculation, like if surface moves, it it transforms. Like surface is here. If it transforms, like I have a surface called V, and it transforms by B, then how much N transform? Because calculation is happening on N, okay, not on V. So if there is a model view matrix transformed by B, then how much N transform? So N dot V. So our model view matrix and N, it's normal. If I see dot, then that is 90 degrees, so that is 0. So if in the model view matrix there is a transformation of B, okay, so B, how much there is a transformation in N, that is A, suppose. Then this formula, what we showed now, it becomes like this, and finally it comes like this. So A is nothing but transpose and inverse of B. So if you see the kind of model view matrix, actual matrix, then first three row and first three column is a kind of rotation, and a right column is transformation. So inverse and transpose are same thing. So if I inverse and transpose, it is same as the model view matrix that we had in V. Okay, so but the translation differs. So whatsoever. So if I transpose, if I transform a model view matrix V by B, then its normal would transform by A, that is transpose and inverse of B. So that is the calculation. So calculation starts from here and goes like this, and then from here again like this. Okay, so for detailed explanation, please refer light calculation, light tutorial, fixed function pipelining. So this is the final calculation that we see. So light at any vertex is emission light of the material, ambience light of the light model, ambient light of the material, and then For each light source is N, for each light source, its attenuation, spotlight effect, and then ambient of the material and light, diffuse of the light and material, and shininess of the specular and specular of the light and specular of the material. And here it is S, here it is L, we described. Okay, in diffuse it is only one, L to N, whereas in the specular L to N and E to N, I to normal, both. So that becomes a surface and surface to N. So this is the net calculation of the OpenGL light and material light component and material component and light model component, everything, how much a vertex should calculate, RGB. So that is the net calculation. So it is kind of so first is emission of the material and ambient light model, ambient material, and then per light source, its attenuation, spotlight effect, ambient, diffuse, and then a specular, and whatever we are getting, power to the shininess. So this much we get. Okay, so we covered this. So in the lab session we will have a kind of light source, projection type, light model, emission, ambient, diffuse, specular, spotlight. So at the beginning we'll see light source and projection type. Okay, so directional light we are using and ortho projection. So orthographic projection we are using and directional light. We can use positional light also, that we'll see. And we are using a kind of a model, and here light is rotating, model is there. Here model is rotating, light is constant, and here light is rotating, model is constant. So light is on the right direction, so we can see the shadow on the left, and light is on left direction, so it is bright. So we see kind of how transformation can happen in light and how transformation can happen in model independently. So that is the idea. So if I have a model, light moves, then I have a model where model moves. So how we can make kind of a balance between them, or how we can achieve it. Okay, so these are light model. If I don't like the light, if I switch off the light model, then how it would appear. Okay, so this one we'll see. Okay, so we start with the introduction, and then directional light, positional light, and light must fall on the vertices. Then light has RGB, similarly we have for material, and light has ambient, diffuse and a specular component. Similarly we have for model also. Emission is extra in the model, and there is a light model which kind of add ambience again. Okay, so transformation is possible in the light source also if it is declared after that model view matrix in the projection. After projection model view, if matrix is defined, then after that if I set the light source, then it is set for transformation. Okay, so calculation for the diffuse and specular. Diffuse only depend upon the light direction and normal, whereas the specular depend upon light direction, normal and the eye. Okay, if I kind of transform a model matrix, then how much normal get transformed, so that we saw. And then the final calculation of the light at each vertices. Okay, so first in the light model we'll see a kind of directional light and positional light and ortho projection right now, and we'll rotate the light and we'll rotate the model. Okay, so we can start. Okay, so we'll write the code. We'll create a directory called GL light, GLSL light. Okay, so directory is empty. Okay, so we can copy the skeleton code what we had written earlier. So okay, so this is the code. Okay, so we'll modify accordingly. So we will trim the vertex shader and we'll trim the fragment shader. So we imported glut, numpy and util-C transformation, and now we have shader program. So we'll remove this and we'll remove this. Now we have vertex shader, fragment shader, compiled shader program, and now we have VBO. Okay, nice one. So here we will place something else in the vertices, and in the normal we will place something else. Okay, now we get attribute location and then we fill the VAO. Okay, so that is the skeleton code. Okay, in the display we translate to -4 and then we'll remove everything. I think it's completely alright. So there is nothing in the code. So here we initialize the glut and we use double buffer and other stuff, and in the keyboard we use util-I keyboard and we pass the transformation, and that's it. There is nothing more. And in reshaping projection we have for this, so we'll use ortho. So instead of perspective, the way we discussed, GL ortho -2.5 minus 2.5 into H by W, 2.5 into H by W 1 to 10. If width is less than height, else GL, else we can copy this only. Okay, so else GL ortho -2 into width by height into width by height okay, so GL ortho -2.5 width by height, 2.5 width by height, -2.5, 2.5, 1 and 10. Okay, if width is greater. So this is what we are using now. Okay, now if it enters the display, then a push matrix and translate and for and GL pop matrix. So it's pretty clear. Okay, now we will use GL uniform location and print. So we have removed everything, only filling the vertex buffer array. Okay, and filling the normal vertex normal, then we'll get the location, and then here we'll fill, and then vertex location and color location. Okay, so VAO, VBO ready, and program linking is ready, and skeleton code is ready. So we need, so we will copy object loader here, and we'll copy OpenGL util here. So we have this much code right now. We'll copy one object file. Okay, so we have whale shark. This is an object file generated through Blender, and it has vertices, and then it has I think vertices are too many. So this much will go in GPU buffer. Then these are kind of vertex textures. Okay, they are again too many. And then these are vertex normal. And then at the end, so GL triangles faces are there. Okay, so that is what it is. Okay, so now we have 4 files. So we'll open our actual code again and OpenGL utility. Here we can say like from opt loader import opt file. Okay, this is to load the opt file. Now we will fill this vertex code. Uniform mat 4 projection, uniform mat 4 transpose inverse model view light. Then we have model view sphere. So I call it a sphere. Model view, I think it would be model, it will be better. Or we'll leave it a sphere. So this is a kind of the actual model view sphere, model view light, but transpose and inverse we discussed. Transpose inverse model view sphere, uniform bool, we want lighting or not, attribute vec3 chord, attribute vec3 normal. Okay, varying vec4 is vertex color, and now void main vec4 color equal to vec4 01. So color is green, means we are hard coding it, color. GL position is projection into model view sphere into vec4 chord 1.0. Okay, now if we use lighting, then what would be the vertex color? Equal to what? Else the vertex color equal to color. So here all the intelligences. Okay, probably we'll develop later. That's it. So we can kind of beautify it. Okay, now here again we have varying in the fragment code, and now we have void main, and here we'll set GL frag color equal to vertex color. That's it. So this is for the lighting. Now we'll move and we'll finish other stuff. Now I think we have okay. So now transformation. Now we have shapes. So like I have a light source and other shape is shapes, and I have a light source, and then I just say sphere, and now this is kind of for X in shape. So this is a kind of hash dictionary, and current shape is light source. So transformation matrix is done. Okay, so here we can kind of enable the shader. So we'll say GL use program shader program, and now we'll for I in. So we have projection, then we have other big names. So or I can make 4YY or 6YY, and okay, so these locations we will know what is the location of this area. So set attr now. So we'll remember the location in this init function object only. So I'll say I plus log, set this to GL get uniform location shader program I, and just set it. So same thing we can do now here. So I can say for I in code okay, so init log and get attribute location. Okay, so set attribute location and set attribute set uniform, get uniform location, get attribute location, and set attribute as init. So we'll remember it. Now we have VAO. So here we have a mat, and now we will kind of read it. So list obj file and whale shark dot obj, what we copied, dot objects dot values, and the first object and its vertices. So mat, we are getting all the vertices. Now for each, okay, so I have 3 unit in vertices X, Y, Z, then 3 unit in normal, and then 2 unit in texture. So there are 3 vertices and 6 its other attributes. 8 coordinates for one vertices. So that is the grammar here. So now we'll push the buffer here. So I'll say kind of buffer np array util c get buffer matrix 0 to 3. First 3 is and total length is 8. Okay, d type dot float 32. Okay, so get buffer, if I give the array and every 8 stride of 8, every 8 beginning to next 3, okay, beginning and then next 3 in 8, so that's what. So I think it's not a bad idea that we'll later print it. So kind of mat some 48 we can print beginning. Okay, now it is done. So same thing we'll set for the here also. So np array util c get buffer mat from 3 next 3 8 where d type dot float 32. Okay, so this is for a normal. So I'll read, this is normal buffer, normal buffer. Okay, now we'll get for init dot code lock. Okay, so this is the location for the coordinate, and init dot normal lock. This is what we have got here, chord and normal I underscores log. So this is what we are pushing in. Okay, we are setting its attribute, and then chord dot log init dot normal log. Okay, so it is normal buffer. So call buffer is gone. Okay, so normal buffer, and then VAO we are initializing, and 2 attribute array, coordinate location, normal location. In the pause buffer we are pushing at the coordinate location and normal location. Okay, so it's not a bad idea to remember few things. Set attribute init and mat and a real mat, and set attribute init va opt vao and vao opt. Okay, so va opt and matrix we are remembering, probably we'll use later. Okay, so now the time has come for this mining. Okay, so what are the things that we have placed here in the kind of vertex shader? So projection, transpose, inverse, model view light, model view sphere, transpose, inverse, model view in sphere. So these are, so first projection will push, slowly we will push everything. Okay, so we are in display. So we'll push here the projection. So GL uniform matrix. So for FV. So we have already pushed attributes. So attributes are pushed at location, init, code lock and normal lock. Probably we can print all the attributes here of the init. Print init attributes for print. Okay, so kind of x 0 plus plus x1 for x in init dict okay, dot items if type of x, if not type of x equal to list. Okay, so we can just print in what are the attributes we have set in the init. So init is a function object, def init. So now we have pushed the attributes. We will push now uniform matrix for FB, and what we want to push is init dot projection lock 1 GL for one value, GL false, and now GL get float V and GL projection matrix. Okay, so GL projection matrix, whatever the GL projection matrix is, we are pushing into init projection. Okay, now this is for GL light movement. So here again, so first we will translate. So we will say GL translate x if length of x equal to 3, else GL rotate x for x in transformation light source. Okay, so at the beginning we have a transformation, that is a kind of hash, that is a dictionary, and in this dictionary there is a shapes like light source and a sphere. For each we have an array. This is transformation array that will be filled in the keyboard. So once we press something, so there is a utility library and keyboard. If we pass transformation, so here we will fill more detail, then we will fill other uniform. Okay, if key equal to tab, then in this case shapes equal to shapes. Shapes dot index, whatever the index of shape is, +1, and then kind of modulo length of the shapes. Okay, so this way we increment the shape and utilize keyboard transformation of the shape. We then will print the verbose transformation. Okay, if R is search, beginning T, so this is for toggling the lighting, so that will also key decode. So key being kind of byte, so we'll convert it to kind of first string object, GL uniform 1I and init dot lit lock 1 if key equal to T, else 0. Okay, so we are done. So this is to invert the lighting. Okay, so now we'll come to our main business. So here we are rotating the, and then we will do transformation in the lighting. Okay, so here it is transpose inverse model view light lock. So transpose inverse model view light lock, and here we will do the inverse. So np transpose np linear algorithm dot inverse. Okay, so this is the grammar is we want inverse. I mean we have discussed it. Okay, so we have to calculate somewhere transpose and inverse. So this is what we are doing. Okay, now GL pop matrix. Okay, so we'll copy this. So we'll do same for the model. So GL translate X, GL rotate. Here I'll say sphere. And here we'll set GL model view sphere, and we don't need to do anything here. Okay, just get the model view matrix. Okay, so here also model view matrix. Okay, now here also model view matrix. Okay, now we have transpose inverse model view light, model view sphere. Model view sphere lock. Okay, so I think we have done with the code. So in the display, first we are translating to -4. We are changing model view. Okay, so probably we'll push it here only. Okay, so first we push the projection matrix to the projection location. Then we change the model view. Okay, we push again and we do some rotation in the model view. And whatever rotation we receive, the transpose and inverse of that rotation. So line algorithm ENV. So that we set in the transpose inverse model view light location. We pop the matrix. We push the matrix again. We do the transformation for the sphere. And then we set the model view sphere location and model view matrix. We set whatever transformation we do for the, here we do for light source, we do for the sphere, and GL matrix 4V, and then it is for transpose inverse model view sphere location. So this is for inverse, transpose and inverse of this model view. Okay, done. So probably we will fill this. So let's understand what's going on. Okay, so what's going on behind the scene? I mean, this is a matter of curiosity. Okay, we are not calculating a specular, we are calculating only diffuse. But we are rotating the light separately and we are rotating the model separately. That is the idea. Okay, so suppose that this is our model view matrix. Okay, so this is the model view matrix, and this is the model view matrix, and this is a normal, and this is the light, and this is the I. So I we don't care right now because we are calculating only diffuse. Okay, how we rotate the light. Okay, so in shaders programming, if we see the shader code, there is nothing light source and rotation, there is nothing like that. Vertex color, only two things we have to decide. Here, what is the position? So, what happens is, when I call display, means when display is called, and then everything, whatever it can push, whatever the data in the GPU, it can change, like it is changing init projection data, it is changing init transpose inverse view light location, it is changing model view sphere, it is changing transpose inverse model view sphere, transpose inverse model view light. And once it is done, then then we have to call the actual drawing algorithm. So we'll say GL bind vertex array and init dot we have kind of pushed it in it, and GL draw arrays, GL triangles 0, length of init mat divided by 8. That's it. So after that, when we call GL draw array, and draw array now it sees the buffer. Okay. So draw array, it sees the VBOs. So we have in VBO, we have vertex and we have normals, and that is bound to, in shader code, that is bound to coordinate and normal here. So in the VBO is a buffer that is stored in the GPU, and one by one in the GPU, one by one it starts calling. Okay, GL draw array. Okay, so in the GPU, whatever is stored, vertex and normal, one by one, so per vertex it will start calling. Okay, divide by 8, because this is how it is. So it will start calling one by one. Now I have to decide what would be the GL, what would be the new position for it. So this code is getting called again and again each vertex in the GPU that we have stored. So for each vertex, the position is projection into model view sphere. So whatever the model we have changed, so new position of the model into code. So what is this line? What is this line? Okay. So suppose that this is okay. So this is a kind of model. Okay, and model has a kind of a point. Model has a point. Now model is rotating. Okay, so we rotated by 45 degrees. Point change. The point location changed. I think it's quite visible. Earlier point was somewhere else. Now it changed its location. Okay, we can try again. Okay, so okay, so here it is at the beginning. Now I'll rotate by 45 degree and it changed. What is the new location of this point? If I do some transformation, that is a big question. So that is this. Whatever transformation we have done transformation. Model view sphere, this is the model view transformation. Whatever transformation we have done, this is a 4 by 4 matrix. And this is 1 by 4, this is 4 by 4 matrix, and this is 4 by 1 vector, means matrix or vector. If I multiply this matrix, new matrix, that is the rotated one, with the old coordinate, it gives us new coordinate. Okay, so model view sphere, that is 45-degree rotated. Okay, if I multiply with the old coordinate, the result is vector of size 4, that is the new coordinate. Okay, so that is the kind of fundamental. Pretty clear. Okay, so if I translate this, again its position change. How much is change? Okay, so if this is the old position, code is the old position. If I multiply this with this transformation matrix, now I did translation, then it will bring a new location. So it will be of same size, same kind of row by column as whatever we have. So it will be kind of vector 4. It's not a matrix. And if I multiply by the new translation, it will result in vector 4 only, but new value will come. So here earlier if it was at position x, and it is at position, earlier it was at position x1, now it is at x2, then this full multiplication will give x2, where this is x1. Okay, so this is matrix multiplication. Okay, so how will rotate light? So light rotation is same thing. If I have a light, okay, now suppose that I have a light, and that is at this location, light normal. Okay, light has a normal. So light normal is at this location. I think it's better to bring at them. Okay, so light normal is at this location. Now if I do translation here, then light has to move. Okay, light should move, means, okay, what I'm trying to show is that how I can move the light source. Okay, now I know that how I can move a kind of a model, how I can move a light source. So I have a kind of a model view matrix, and if model view matrix is kind of, if I am changing the model view matrix, okay, then what I need to do, that light source will come here. Okay, because light source I want to move the way model view matrix is moving. So what I need to do? Okay, how I can move light source? So the idea is that I can go for same multiplication. Model view, if it rotated, then if I multiply this model view with this light source old position, it will bring the new position. But I have to multiply with the normal. Okay, it's a normal. Okay, not the actual matrix. So I have to bring the transpose and inverse of whatever the model view, if there is a transformation of B in the model view, inverse and transpose, if I calculate, that will be, this is again a matrix. If this matrix, if I multiply with the old location of this light source, it will bring the new location of the light, the normal. Okay, so if I understand this formula, then I can calculate the vertex color. Okay, so vertex color is vec 4 color.rgb into dot normalize transpose inverse model view sphere into vec for normal 1.0 dot xyz normalize transpose inverse model view light into vec 4, okay, and then 0 0 0 0 x y z color dot a. Okay, so if I have a vertex normal is this, how much normal would move if I move the model view sphere? Okay, it will move transpose inverse model view sphere into vertex normal. Okay, now we calculate xyz and we normalize it. Same way, transpose inverse model view light, and this is the light position original 0 0 and 10 in the kind of that direction. This is 0 means directional light, and now xyz and we normalize it, and finally we do the dot these two. So two normals we are doing dot. This is what we are doing. Okay, one is light normal, okay, one is light and one is a normal. Okay, so we are doing actually this a dot n and b dot v. So okay, so we are calculating this diffuse. So light normal and vertex normal. Okay, this is vertex normal, but due to transformation matrix this normal is changed to this much. Now this is our light normal. Due to transformation matrix this change this much. Okay, that is the new vertex. Okay, so this is the way vertex color is changing. So if I see this, we go to the previous location. Okay, and if there is a vertex, okay, so if there is a, what would be the vertex color here? If light is falling here and model is rotating, so right now the light is falling on the vertex but model rotated. Okay, now light is not kind of stayed there. So this normal is this, normal is in this direction, light is falling in this direction. So this is the theta, the angle that we have to calculate the dot. So light angle and its new normal angle. So the new normal is this, normal into transpose matrix. So light we are not changing, light location is same. So certainly this color would fade because it is going in the angle of the light. Okay, now this is fixed. What about if I move the light? Okay, I move the light here, then again it will fade more. Okay, the angle is growing, so cos theta is less. So if normal is fixed, now we are not changing the normal, but like inverse model with light is changing. So this is becoming lesser. If this is becoming lesser, I mean this is going away, then this dot what we are calculating dot, so dot will be smaller. So vertex color will be fade, it will be less. Okay, so this way, so we can try executing it. So we'll go by the code what we have done probably. Okay, so we have numpy array, object loader and util-c, and light source and a sphere is there. Current shape is light source, transformation matrix is ready. And here we have uniform matrix 4, projection, transpose in model light, sphere, and lit, and coordinate normal, varying is vertex color. Color we have fixed as green, and then position would change the way model view sphere is changing. There is no transpose inverse here because it is not normal, it is a simple coordinate, we are modifying it. And then vertex color would change the way we change the transformation, we change the model view sphere, and we change the model view light, and that's it. And then varying vertex color, the frag color is that much well. Now we compile it and we use it. Now we get the position of projects, all these uniforms and attributes. Then we have a matrix of our object file, and then we set up VAO, VAO1, VAO2, and after setting up, we set the VAO, okay, and then we remember the matrix and VAO option, we print it, then we go to display. First we push the projection, and then we do the transformation as the light source, and whatever the model view matrix is, we do the inverse and we set it here. Then we pop the matrix and push again for the transformation in the sphere, and then we set the model view matrix in the model view sphere, okay, after the transformation, and then we set the model view matrix transpose and inversed, that is in the view, okay. Then we bind vertex array, we draw it and pop it and pop, that's it. Okay, so hope for the best. Okay, something unmatched. Location, GL flow. Okay, we'll try again. Okay, expected end of the file, fragment shader, line number 6. Okay, again in the fragment shader, expected end of the line. So this is the end of the file. Vertex shader main else. So this is main, and here I think that is all, we don't need this. So this is the main, that is the end. If not, we will get program IB shader program link status, print error, GL get shader info log shader program equal to. Okay, so probably we have done something here. Version bearing main DL pack color vertex color. Okay, so probably there is a semicolon here we have missed. We have not printed error or error. Okay. Vertex shader. Okay. Okay, GL get buffer data NP array util C get buffer mat. Did you mean type? Okay, so this is matrix we are talking about. So first 3 is vertex, next 3 is normal, and next 2 is texture. Again 3. So there are in 8 combination things are there. 25. GL buffer data NP array util C. Okay, so D type equal to NP dot float 32. D type equal to NP dot float 32. Okay, so this is probably string. Oh, so we are getting. So this is the light. Okay, but no light calculation. Shape is referenced before a segment. Okay, so global transformation shape and shape. Okay, and lit location we have set already. No? Okay, so we'll set at the beginning only, it should be lighted. Or okay, so we'll set it the way it is. Okay, so I'll press T, it will light, not light. Okay, so there is something called import RE, regular expression. Lit lock. So we will do the kind of lighting at the beginning only. So here in the code, after doing all the operation, so I'll say that lit is 1 at the beginning only. So we won't print the mat. We are still printing the mat. Mat. Okay, so for X in X init dict items, if not type of X equal to list, for those only. If not type of X 0. Okay. If not type of, so this is value. Okay, so we are getting it. So this is kind of, now if I press V, there are two shapes. So if I press V, it will print that. Oh. So here I can print the shapes of, so what is the current shape and what is the transformation. Okay, so now if I press V, so these are the locations it printed. Lit location is 4, 3, 2, 1, 0 and coordinate is 0 and normal is 1, V of is 1. Now current focus is on light source. So I'll try to rotate the light source. Okay, so I'll press Y. Now the transformation is 90 and Y axis. So light went on right side and it became dark kind of. Okay, now I press tab and focus is now a sphere. So now a sphere matrix would move. So if I press Y, then now right side light is there. Okay, I can kind of okay, so light is on right direction. Now the focus is on sphere. So this is a transformation matrix. For light source, it is 90 degree it is rotated, whereas sphere has done this much. Okay, now we'll rotate the, so I'll press tab, now focus is on light source, we'll rotate the light. Now light went completely back. Okay. If I print, then it is 270 degree. So it came on the left side. Now I can rotate the fish. Light is on left side. It can be seen. Okay. Now I'll press tab again, and if I press V, then now I'm at light source. So whatever I do, I'll rotate the light source. I'll rotate again the light source. If I press V, 350 degree, one more time. Okay, so light 360 degree. So light has come in the kind of in the positive Z direction completely. I can rotate the light again. I can rotate light in the Y direction I was rotating. I can rotate in X direction. Light is going down, but model is not moving. Okay, now if I printed it, then 100 degree it has rotated. So minus X 90 degree. So X has rotated 90 degree and Y is 360 degree. So light is down. Okay, now if I rotate this guy, light is below the scenery. Okay, I can bring the light up. if I press V, okay, light is, X is 0. Now if I keep pressing X, it will go up. Minus 70 degree. Minus 90 degree X direction and 360 in Y direction. So light is exactly above. So if I rotate it, light is above it. So down the line it is dark. Okay, so this phenomenon we can see in the sphere also. So here whale, okay, shark object. So I can change it to kind of a sphere. I have a sphere object, so I'll copy it. So I'll try again. Okay, now I am in light source mode and there is nothing in the transformation matrices. Now I can move the light. Okay, so it will be kind of more clear if I make kind of GL clear color as kind of some essence will give like a blue. Okay, so it will be more clear. Now I can move the light. Only light is moving. Okay, now I can move the sphere now, but light will. Sphere is actually rotating. We can't see, so I can translate it. Light is there only. I can rotate, but I can translating. I can rotate, but it is not visible. Okay, now I can rotate the light in X direction. Okay, so transformation matrix is crossing the okay, so we'll make little bigger. So here we set 1 to 10, we can set 1 to 20 somewhere. And here at the beginning we'll set it to some 10. Okay, and now I can rotate the light in X direction. Okay, so this is a fixed coordinate and this is grand coordinate. This is what we want. Okay, and in Y direction we can translate the way we want. Okay, so we can bring in the whale again. Whale, shark, and we can see kind of ocean kind of. This is the whale shark, and we can rotate the light, and we can rotate the shark in the light. Okay, so it's time to rotate the light. And Mr. Sark is with me. Now light is not rotating, but the Sark is rotating. Okay, so we'll kind of see the lighting enable and disable. So we have this file. So keyboard, if I press T, then kind of it will switch the lighting. So that feature we'll see. Okay, so by default lighting is enabled. Okay, so by default we had set in the init only, lighting is enabled. But in keyboard function we can change it. Okay, so by default lighting is enabled. So lighting is coming from +Z direction. Okay, so this is the position. Now I'll press T. Okay, so I'm pressing T. So small t is for enabling the light, capital T is for disabling the light. So this is light is disabled. Lighting is disabled. This is what we are kind of seeing here. So in this diagram the light is from right side, this diagram light is from left side. And if we disable the light at all, okay, whatever color we are just passing. So if I see the program, so in the shaders code, we have if lighting is disabled, if lighting is not there, then we just pass the color, whatever the green color is. Okay, so this is what we want. Okay, so I shall kind of okay, so I'll disable the lighting, so I'll press capital T and light is not there. Now I have the transformation. I have the transformation, but lighting is not there. So if I go to light mode also, Okay, now the mode is light source, and rotate the light. Whatever I do, I am pressing X, Y, Z to rotate the light, nothing is happening. Okay, so in sphere mode, though I can do all the transformations. Okay, so if I press a small t, then lighting would appear. So this is the position of the light. So probably light is coming from the right direction. Okay, I'll see where I am. So it is sphere mode. So I will press tab, and then I can rotate the light. Okay, this is how it is. Okay, so this is again I can press, if I press capital T, light is gone. Light comes. So this is about the lighting. I can change the color also. So color whatever we had taken, so it is kind of initially green. So I can make it yellow. Okay. So the shark is yellow.